It sounds like a mistake. A mission designed to carry humans around the moon is deliberately placed on a path that offers no way to turn around. No abort, burn to come straight home. No mid-course correction to escape the route. According to NASA, once Artemis 2 commits to its trajectory, the crew is effectively locked into it. That shouldn't happen. Not in modern spaceflight. For decades, safety has meant flexibility, redundancy, the ability to change course if something goes wrong. But this mission does the opposite. It removes that option and replaces it with something far more unsettling, a trajectory that brings the crew back, only if everything follows the laws of physics exactly as expected. No shortcuts, no second chances, just a path that either works perfectly or doesn't work at all. Space missions, especially crewed ones, are built around control. From Apollo 13 to modern orbital flights, engineers design trajectories with multiple escape options. If something fails, astronauts can fire engines, adjust course, and return early. Flexibility equals survival. That has always been the rule. Even missions to the moon traditionally included contingency plans, free return paths as backups, not as the primary design. Because relying entirely on gravity alone, that feels risky, almost passive. And in human spaceflight, passivity is usually avoided. Control is everything. Until Artemis 2. The first hint that something was different came from mission planning documents. Artemis 2 wasn't just including a free return trajectory, it was built around it. Meaning the spacecraft would swing around the moon and return to Earth without needing major engine burns. At first, that sounds efficient, even elegant. But then comes the detail that changes everything. Once the spacecraft enters this path, there is no practical way to stop or reverse it. No turnaround point. No easy exit. Which raises an uncomfortable question. Why would NASA choose a trajectory that removes control instead of adding it? To understand this, you have to understand what a free return trajectory actually is. It's a path shaped entirely by gravity. The spacecraft leaves Earth, arcs toward the moon, swings around it, and is naturally pulled back toward Earth, like a perfectly thrown boomerang. No propulsion required for the return, just physics. In theory, it's one of the safest trajectories ever designed. Because even if engines fail, the crew still comes home. That's how Apollo 8 and later missions ensured survival in worst-case scenarios. But here's the key detail. In Apollo, this was a backup. In Artemis 2, it's the main plan. This creates a strange contradiction. On one hand, a free return trajectory is incredibly safe because it guarantees a path home without engine burns. On the other hand, it removes flexibility because you can't easily deviate from it once committed. Safety through rigidity. That's the paradox. Modern engineering typically avoids single-point dependency, yet Artemis 2 embraces it. The spacecraft's return depends heavily on precise initial conditions: launch timing, trajectory insertion, gravitational alignment. Everything must be exact. Because once you're on that path, you're no longer steering in the traditional sense. You're falling. And the consequences of that design choice are bigger than they seem. Because space is not perfectly predictable. Tiny errors, fractions of a degree, seconds of timing, can compound over hundreds of thousands of kilometers. A slightly incorrect trajectory could mean missing the optimal lunar swing by, re-entering Earth's atmosphere at the wrong angle, or returning too fast, or too shallow. Each of those outcomes carries risk. And unlike low Earth orbit, there's no quick rescue, no immediate correction. Once Artemis 2 is on its path, the crew is committed for days, alone, following a trajectory that must work, because there is no alternate route waiting in the background. NASA's explanation is straightforward. This trajectory is chosen for safety. By relying on gravity instead of propulsion, Artemis 2 reduces dependence on engine performance during critical phases. Engines can fail. Physics does not. A free return path ensures that even in a worst-case scenario, loss of propulsion, the crew will still loop around the moon and come back to Earth. It's a design rooted in the lessons of Apollo. Simple, reliable, tested. And at first glance, it makes perfect sense. But then, mission details added a complication. Unlike Apollo's early flights, Artemis 2 is not a perfect free return throughout the entire mission. There are planned adjustments, trajectory refinements, subtle engine burns to optimize the path, which means the mission isn't purely passive, it's a hybrid, part gravity, part control. And that changes the equation. Because now, the mission depends on both. The natural trajectory working as expected, and the spacecraft executing precise corrections along the way. It's no longer just physics brings you home. It's physics brings you close enough if everything else works too. And that reintroduces uncertainty. The Orion spacecraft will travel farther from Earth than any human-rated spacecraft in decades. Navigation relies on deep space tracking, not constant real-time control. Communication delays increase. Autonomy becomes critical. At the same time, re-entry speeds will be higher than typical low Earth orbit missions, meaning the margin for error narrows. Each of these factors alone is manageable. Together, they create a system where precision matters more than ever. And yet, the trajectory reduces the ability to respond dynamically. Which raises a deeper question. Is this design purely about safety? Or is it about testing how much we can trust physics alone? Within the aerospace community, this approach isn't universally viewed the same way. Some engineers argue this is the safest possible design, minimizing reliance on complex systems and maximizing natural return paths. Others see it differently. They point out that modern spacecraft have far more capable propulsion and navigation systems than Apollo ever did. So why lean so heavily on a rigid trajectory? Why not design for both safety and flexibility? There are also debates about mission philosophy. Is Artemis 2 primarily a test of systems, or a demonstration of deep space operational confidence? Because depending on the answer, the trajectory choice means something very different. Either way, one thing is clear. This isn't just a technical decision. It's a statement about how we approach risk in deep space. In the end, Artemis 2 is not just a mission around the moon. It's a return to a deeper idea. That sometimes the safest path forward is one you cannot control. A trajectory defined not by constant correction, but by trust. Trust in physics. Trust in calculation. Trust that if you enter the path correctly, it will carry you home. But that trust comes with a quiet trade-off. Because once you commit, there is no turning back, only forward. Around the moon, through the darkness, and into a future where exploration may depend less on control and more on understanding the forces we cannot change.